We ended our last video with a lot of technical details about RSA cryptography, encoding and decoding. So I'd like to start this video with a recap summary, returning to our great pictures that we have. So remember that we have Alice and Bob is going to broadcast what kind of box and lock are required in order to send him messages. Now we're going to use a very small example just to make the computations very easy. Bob is secretly within his head going to pick two prime numbers. Here we've chosen P to be 7 and Q to be 13. We've multiplied them together and that gives us our N. We've then very quickly and easily computed P minus 1 times Q minus 1, since Bob already knows what P and Q are, to get this number 72. And then Bob has selected, by a sum method, often a random selection, the number 11, because 11 is a number less than 72 that is coprime to 72. So nobody knows this information but Bob very loudly advertises that N is equal to 91 and the E is equal to 11. So Alice comes up with a message that he wants to send to Bob. Alice begins by writing his message and translating each of the letters to a numerical value, remembering that A is starting at 2 and then we're counting up from there. Now, because Alice can take a look at Bob's sign, Alice knows how to encode these letters. He's going to take 2 and raise it to the 11th power and then mod that number by 91 in order to get something like 46. Or 9 raised to the 11th power is 81 when we mod it by 91, and so on and so forth down the line right here. And this last line right here is all that's going to be sent very publicly to Bob. Now Bob receives that message, and if Bob wants to decode that in order to figure out what Alice wanted to send, Bob is going to use his secret and private key, D, which is 59, which was selected so that 59 times 11 would be congruent to 1 modulo 72. This special number that we found from the P's and the Q's earlier. All of that is computationally easy for Bob since he is the one with knowledge of P and Q. Now, all Bob needs to do to decode the message from Alice is take the encoded text, which he has the numbers for right here, and each one of these numbers will be raised to the dth power and modded by his public key, 91. So 81 raised to the 59th power, then modded by 91 should give me 9. 46 raised to the 59th power and modded by 91 should give me 2, and so on and so forth. Then Bob uses that standard key to go from these numerical values to these letters. Now, the thing that's important here is that Eve, any eavesdropper, could have watched this whole process transpire and had access to this message. One of the things we need to think about with any public key cryptography system is just how secure is this message from being intercepted from somebody like Eve. It's true that Bob didn't have to advertise or send any method of encryption to Alice, so there's no way that he sent information of the key to Alice, so Eve could not have intercepted that, but could she secretly build her own key? So there are a handful of ways that we generate very strong RSA codes, and because everything is public and because computers get faster and faster from year to year, we need to be confident that when we build this number n, we build it out of two very, very large prime numbers. So standard kinds of cryptography that you're going to see using RSA over the internet are going to use primes that have about 1,024 digits apiece. So huge numbers in order to make this process so time-consuming that even though we know theoretically how to crack the code, it's just not feasible with the amount of time that we have. Now, any eavesdropper does have knowledge of the value for E. Figuring out what P minus 1 times Q minus 1 is would be a very monumental task that by itself would be time-consuming, but without knowledge of how n factors, there's really no way to search for what this D value might be other than just a loop that goes through all of the possibilities. And with the magnitude of the numbers that we're seeing, that's just not feasible. However, what makes all of this work is that because Bob has knowledge of the P and the Q, and therefore knows P minus 1 times Q minus 1 very easily. Bob is able to use the Euclidean algorithm and Bezout's identity in order to find D in a significantly more effective manner. Now remember that Bezout's identity and its use in the Euclidean algorithm was to say whenever we have two numbers and we use the Euclidean algorithm to find their GCD, we can then backtrack up from the Euclidean algorithm to write that GCD as this integer linear combination of the values. In particular, when we apply that to E and then this number P minus 1 times Q minus 1, we can find integers S and T so that E times S plus P minus 1 times Q minus 1 all multiplied by T is equal to 1. Now, just think about taking this equation that we know we could obtain from the Euclidean algorithm and think about modding every term that you see by P minus 1 times Q minus 1. When we take a look at this second addend, that's a multiple of P minus 1 times Q minus 1. So this second addend is congruent to 0 mod P minus 1 times Q minus 1. 1 mod something really, really huge is just 1. And then we've left this right here, but just included the modulus right here. So whatever this S value is, when we mod it by P minus 1 times Q minus 1, that value is the D that we're looking for in the Euclidean algorithm. That's our private key D. And the Euclidean algorithm uses logarithmic growth as opposed to this linear growth that we're going to see just looping through everything that we have. Just to summarize, because Bob has this prerequisite knowledge of P and Q, he was the one who selected them. All of these computations using Bezout's identity and the Euclidean algorithm will be very quick for Bob, and he will not have any trouble making this kind of computation. Any eavesdropper is going to have to go the slow way around, factoring n by hand, which is very time-consuming, before the eavesdropper has the ability to find this D through the same method. And that's what's going to slow up our eavesdroppers, not the fact that they don't understand what's going on or that they don't have the key. What slows them up is the algorithmic complexity and the large scale of the numbers that we're looking at.